NASA researchers are exploring how to grow buildings on Mars using mushrooms. Their concept: ship compact structures containing dormant fungi, add water, and watch habitats develop around pre-designed frameworks like biological construction systems. Researchers are testing mycelium composites for protective applications and fire-resistant cladding. Ecovative has commercialized millions of mycelium packaging units since 2011. IKEA has piloted mushroom packaging in multiple markets, and the Netherlands built the Growing Pavilion in 2019, featuring mycelium-based walls and roof panels that got partially composted when the exhibition ended. So we're talking about mycelium, and it's reshaping how we think about construction, packaging, and sustainable materials. The whole premise sounds wild. You're telling me the fuzzy stuff growing under rotting logs can create building components? That we can toss agricultural waste into a mold, wait a week, and pull out fire-resistant panels? That fungi, the same organisms that give us athlete's foot, could help tackle both the construction industry's carbon emissions problem and material waste simultaneously? The numbers behind construction's impact are stark. Traditional building devours roughly 40% of global resources and generates about 39% of energy-related CO2. Housing costs have outpaced wages for over a decade. The industry needs alternatives, and mycelium offers properties that sound almost fictional. It forms protective chars at high temperatures while weighing a fraction of traditional materials. Let's start with what actually happened in 2014 at New York's Museum of Modern Arts. Architects from the living showed up with around 10,000 bricks grown from cornstalk waste and mushroom roots over 2 weeks in upstate New York. They stacked them into Hi-Fi, a 12-meter circular tower that stood for a summer season, structurally stable as a temporary pavilion, aesthetically striking. No cement, no mortar. Here's the underlying process. Take agricultural waste, sawdust, hemp stalks, coffee grounds, literally the stuff farmers burn. Mix in fungal spores. The mycelium, the underground root network of mushrooms, starts growing. Those thread-like structures called hyphae spread through the waste like nature's 3D printer, about 2 to 10 micrometers thick, weaving through every particle. The fungi release enzymes that break down organic matter while their thread network binds everything together. Pour this growing mixture into a mold, any shape you want, and wait 5 days to 3 weeks, depending on density. The mycelium fills every contour, creating forms that would cost a fortune with conventional manufacturing. Once it reaches the right density, heat it to around 60 to 80 degrees Celsius. This kills the fungus, evaporates moisture, locks in the properties. What comes out won't sprout mushrooms in your walls. It's a stable material you can grow to order with targeted density and insulation characteristics. When Hi-Fi came down after its summer run, they composted the bricks. Try doing that with concrete. Eben Bayer and Gavin McIntyre saw the commercial angle and founded Ecovative in 2007, targeting packaging, a direct replacement for styrofoam. Dell started using their mushroom packaging around 2011. IKEA followed with pilot programs across multiple markets. Major corporations betting on fungal materials meant this wasn't just an art experiment anymore. The material properties made engineers take notice. As insulation, mycelium composites show thermal performance comparable to polymer foams. Fire testing reveals they form protective chars and release less toxic combustion products than many synthetic foams, a genuine safety advantage for interior applications. Now let's address the strength question, because this is where people get confused. Mycelium composites typically deliver between 0.1 to 0.4 megapascals in compressive strength, roughly 30 pounds per square inch. Concrete crushes at 20 to 40 megapascals, around 4,000 pounds per square inch. In a head-to-head strength contest, concrete wins by orders of magnitude. But mycelium composites weigh dramatically less, often 80 to 300 kilograms per cubic meter depending on formulation, compared to concrete's 2,400 kilograms. This isn't about replacing foundations or high-rise frameworks. It's about non-load-bearing walls, insulation panels, acoustic treatments, interior elements where lightweight properties provide advantages in transportation, installation, and reducing structural loads. The 2019 Growing Pavilion in the Netherlands pushed applications further, mycelium-based panels for walls and roofing, showcasing bio-based construction across European design exhibitions. Architects started requesting custom applications for specific projects. Meanwhile, startups were multiplying globally. Mycotech in Indonesia was producing furniture and building panels. Mogu in Italy was manufacturing acoustic ceiling tiles and flooring getting installed in commercial interiors. MycoWorks, a separate company in the mycelium materials space, partnered with Hermes to develop fine mycelium leather that debuted in a limited Victoria bag release in 2021. The waterproofing challenge and lack of mechanical performance nearly derailed commercial viability. Mycelium can swell in humidity. Researchers explored various treatments: chitosan coatings, nanocellulose reinforcements, hybrid composites, combining mycelium with bamboo or hemp fibers. These approaches showed promise in lab settings for improving water resistance and mechanical performance, though standardizing them for commercial production remains ongoing work. Each solved problem opened applications. Acoustic panels for studios and performance spaces because mycelium naturally dampens sound. Insulation that performs without chemical off-gassing. Packaging that protected electronics through shipping then got composted. Fire-resistant cladding that chars rather than releasing toxins. But NASA's myco-architecture research is where this gets genuinely ambitious. Researchers are developing concepts for lunar and Martian habitats using mycelium. The idea? Ship a compact structure containing dormant fungi. Unfold the framework on location. Add water, which you're producing locally from ice. Let the fungi colonize around the pre-designed structure over weeks, creating insulation and additional structural support. Once complete, bake it to kill the organisms. You've got a habitat with biological insulation and potential radiation shielding properties. Simulations suggest the hydrogen-rich, carbonaceous nature of mycelium could provide radiation protection advantages. Self-repair through controlled living cultures is being discussed as a future possibility. NASA's investment in this research validates mycelium's potential for extreme applications. They need solutions that work in resource-constrained environments with minimal shipped mass. Mycelium offers both. The regulatory path remains challenging. Building codes were written for concrete, steel, and timber. Mycelium projects face case-by-case approvals where each application proves safety from scratch. Regulatory bodies designed for conventional materials move slowly when confronted with biological innovations. Manufacturing scale presents hurdles too. Current production is limited by growth rates and substrate consistency. Meeting broader construction demand requires optimized fungal strains, standardized recipes, and automated facilities with monitoring systems. But momentum is building. Several EU countries are developing frameworks and incentives for bio-based construction materials. Startups raised significant funding in recent years. Construction firms are running pilot programs. The technology is moving from experimental installations toward commercial viability. Environmental regulations keep tightening. Construction costs keep rising. Climate pressures keep mounting. Mycelium offers solutions that align business interest with environmental benefits. We're watching the construction industry, one of the most conservative sectors globally, seriously explore growing components instead of only assembling them. That shift alone signals how much pressure the status quo faces. This isn't about mushrooms saving the world overnight. It's about discovering that one of nature's most widespread organisms might help solve problems we're spending billions addressing through industrial processes. From temporary pavilions to potential Mars habitats, from packaging to interior panels, mycelium is carving out its niche. The path from lab to market is never straightforward, especially for materials that grow. But watching architects compost a tower in New York, seeing acoustic panels installed in commercial buildings, and reading NASA's research proposals suggests we're past the will it work phase. We're solidly into how fast can we scale this? And honestly, if researchers can seriously propose growing habitats on Mars with mushrooms, Earth applications should be straightforward.